Alright, so we have finished the constraint network, and they're doing what they're supposed to be doing, where they break at a proper time and then they hold when on some random pieces. So right now we're gonna actually cache this simulation out. A file cache could be good enough. Sometimes people use ROP Apple driver. I guess file cache is good enough. Don't want to introduce complications to what we use here. Just file cache should be doing the job quite nicely. I'm gonna use the geometry file type to be in the hip file geometry folder, right? And then I'm gonna name this guy base simulation cache. Okay, we have that much frames. Just go for shift disk, and that's gonna go through the simulation and then cache our simulation into files so we can load them later on without having to simulate every time. Okay, I'm gonna wait for this to finish, and when we're done, we can move on to upresing the pieces. Alright, our cache is done. Let's go check on load from disk. Then we can go through the timeline to look at the simulation results. Okay, pretty cool, right? So we can go ahead and really start to do the upresing part. Let me go to the object level and disable the visibility of our previous steps. Let's go ahead and drop down a new geometry for the upres part. Okay, now this new geometry here will be named to geo upresing, right? And here inside of it, I'm going to delete the file. We're going to go for a object merge. Now we're going to merge in the original pieces before we pass that into simulation. So let's go back to the destruction here. Now that piece is actually here, right? So before we do simulation, so right click on that dot. Let's create a null here. I'm going to name this null packed. That's right before we pass the geometry, the packed geometry to the simulation here. Now we're going to read those pieces and upres these guys and replace that on our simulated result. So here after object merge, we're going to actually load it here, right? So let's see, it's fract packed right here, right? So that's the packed result. Again, the pieces without any simulation yet. And then we're going to drop down a delete. Now this is actually a way we can delete some of the pieces using the timeline $f. Just going to delete one of the pieces. Now why we can do that? Because those again are points, right? The packed points. Every point have a ID number. The $f is a number, so it's going to delete the piece with this point number here. So I'm going to actually go for delete non-selected. That's going to isolate actually every individual piece when we go through the timeline. We have 7,000 pieces, so that's only just 115 pieces here. So we're going to actually unpack these guys to get the actual geometry, and then we're going to remesh it. Okay. And we're going to change the target edge length to something really small, like 1,001 or so. And then we're going to use the hard edge group. We're going to look for the inside and the outside so that they're having hard edge on the edge. Okay, so this is basically the same shape but rematched to a more complicated geometry. If you look at the geometry now, we have that much point, right? It's okay to have that much point if we only have one piece like this, but we have, remember, 7,000 pieces. Now every piece is this dense. This is going to be a unbelievably high dense geometry if we put them all together, right? It's 4,000 typical piece like that times 7,000, right? It's millions of polygons. I don't think ZBrush can even handle that. It's a very high resolution data mesh in this case. So we are gonna actually simplify it as much as we can. Now if you really think about it, we wanted to add detail on the inside. We don't really want that much on the exterior, right, the outside faces. So let's actually simplify the outside face. Right here I'm going to drag down a delete. Okay, so this delete, I'm going to delete the group inside, and operation will be delete non-selected. That's going to give me the inside. Holding down Alt and drag it to the other side, I'm going to change the group to outside, and that's going to isolate the outside for me. Now I'm going to keep the inside the way it is. The outside though, I'm going to actually simplify it by doing a divide right here, and this divide should allow me to use the remove sharp edges, and that's gonna actually make it a simple model like this. Again, we still have the points. Anyway, the normal is kind of wrong, so let's drop down a normal to fix that. Right, it's better now. And just for consistency, we are also going to do a normal here on the other side, so they're all having proper normal. Now we can merge them together. Okay. Now we have a piece that is empty here on the outside face and more complicated on the inside. And then we can fuse them together because they're separated earlier. Now it's one piece of geometry. As you can see when you drag it, it's connected. I don't really need that added. Alright, now just to check the pieces, right? This piece is okay. Let's take a look at other pieces. This one doesn't seem so hot, right? And this one is going crazy. Now why is that? Because this divide destroys a lot of detail inside. So we actually have to tell it when the face are not as simple as just a face, flat face like what we were having earlier in that piece we were working on, right? Some pieces are more complicated, so we have to use some trick to actually not deleting the lines. Now one of the ways we can do is break the faces before we break it. We divide it so that the bricked faces will remain their edge. So here I'm going to create a attribute wrangle. Okay, and here I'm going to load in the unpacked result geometry as the second input, this guy. And here instead of it, I'm going to work on the primitive level. Okay, and then I'm going to search for the closest face. Now there is no near face. We have near point right now. We don't have near face, so we have to actually get the near face using another function called xyz dist. So xyz distance. Okay, now this function is a little bit complicated than the function we have used before. If you look at the documentation for that, xyz distance vex function, the signature is this. Right? We're going to use this second one. It needs the geometry, it needs the point at the position, right, where we start searching, and it will have two pass by reference argument, which will be the return type. It will return primitive, a number of the nearest primitive, also the UV of it, which we don't need, but because this function have this signature and it's more like a C style kind of like function, so we do have to give it something here. And they're passed by reference, so whatever you pass in will be changed. That's how the return works here, because in a generic function that is C style, you have only one return type like this. If you want to return multiple things, you cannot just return A, B, C like Python does, right? You can only use pass by reference to kind of like changing the things you passed in, and to get information back using that way. So whatever argument or variable I passed in here, if you have an ampersand in front of it, that means that argument you passed in will be actually passing in the physical address in the memory of that variable and directly change it inside of the function. So whatever is done to this guy inside of the function is done to this guy. Okay, so I'm going to create those two reference pass by reference arguments. So int prim num let's call it near prim num, right? Near prim num. I don't even have to initialize it. It will automatically initialize it with 0 because it does that. Not sure if you can do this. Nah, you cannot. Anyway, so nope, it's not actually C++. But anyway, int near point primitive is there. Let's initialize it just in case. It equals 0. And then also a vector is another signature here, right? So right, vector alt uv equals to let's just make it use the default constructor to construct this vector. So xyz distance here, we're going to use the first the second geometry, right? We're asking that, and then the position will be our position. So at p will be the one we use. The primitive will be the near primitive number. Again, this number will be changed by the function, and the alt uv will also be changed. So whatever after this function, this guy, this variable will be actually the near point, the point number of the nearest face. Okay, I hope this makes sense. Oops. There's a comma here, so 1 comma. Right. And then we got that. We're gonna use that as a attribute. So I at original prim id or prim num will be equals to that near point num. So we have a way of telling that for any smaller triangle here on this geometry, let me delete that, add it. For every smaller triangle on this geometry, what's the original face, original bigger face, like this bigger face here? What's the face number of those triangles? So for every triangle inside of this loop I'm selecting now, we'll have this attribute called prim num id, right? Original prim num, right? That attribute, the same attribute, which is the primitive number of this face from the original geometry. Let me delete that. Okay. So now because of that, we can do a primitive split. And what this allows me to do is now using that attribute called original primitive number. And what that does now is it's going to break the geometry based on that ID. So different ID will be broken into 2 pieces. If you now go to select and use 3D connectivity here, you can see now they're break into different islands. And because they're break, the device will not be able to destroy it. It will keep those edges. And then we do the normal to fix that. We probably need to fuse them together here. Alright, cool. Now we have a proper face no matter what piece we're going for. This face will be good. That's not good actually. Not sure why. Maybe I was selecting something. Let's just turn on the colorize. Divide. Huh. Not sure what's happening here on this guy. Maybe I have some bad geometry over there. Really? Let's take a look at the original geometry. Original geometry is fine. Just one face, right? Using primitives, getting the first one. That should be one piece also. Primitive split should give us one piece. It's giving us all different pieces for some reason, 2 type of faces. Ln 0, 1, 2. Actually, these guys. Why is it doing that? Let's take a look at the attribute wrangle. Go to geometry spreadsheet. 0, 1, 0, 1, 0, 1, 0, 1. Have 2 pieces. maybe we have overlapping pieces, faces. My geometry is not clean enough. Sometimes that happens. So clean up the geometry is important. Anyway, let's just ignore this guy. Before we pass that along, let's also do another remesh. Right? And for this remesh, we're gonna remesh it with, toggle to a different geometry. We're gonna remesh it to a smaller length again by using input point only. Right. So that's gonna give me, a proper triangulated face. We can actually crack that up to something higher, so we can get smaller faces or lesser faces. Now we can see a geometry that is denser on the inside and simplified on the outside, and it's all triangulated. Everything works quite nicely now. Right? So we went through all these troubles again just to get a simpler geometry. Now this is particularly important. Let's don't update point no more. I'm not sure what that guy is doing a little bit. Maybe that's because it's normal here. Anyway, so just to get, that's particularly important or useful when you are actually creating a wall, right? A wall is having a much thinner inner face and a bigger outer face, and if you can do this simplification, your model could be significantly smaller polygon wise. So that's why we're doing this, and in the next tutorial we're actually going to go ahead and do the detailing on the inside. Okay, see you next time.